Hi, guys. How's it going? All right. So this lecture is on reinforcement learning. So far in this course, we've talked about a lot of different things, and most of them have on some level been about understanding the world, and now we're going to sort of move on to interacting with it. So the lecture is going to first of all lay out the basics of what reinforcement learning is, what the problem that we're trying to solve is, and then we're going to go on to sort of the most recent major breakthrough approach to reinforcement learning, and then we're going to talk about how this field is moving forward right now and in the next few years. Okay, so there we go. So just to clarify how reinforcement learning relates to the previous problems that we've tackled so far. So we've talked about supervised learning, which is that we have data, and we're trying to find the labels that match that data, right? We've talked about unsupervised learning, where we have data, and we're trying to understand the data itself. We're trying to understand something about the distribution of the data. Now, this last problem, reinforcement learning, is given data, we want to pick actions that are going to yield the maximum long-term reward from those actions. Now, without even knowing how we're defining the problem, the last case might seem like might seem very similar to supervised learning. Given data, I just want to pick the best action, right? And so really, I could probably just learn a function that goes from the data to the action. The problem with this approach is that I don't know what the best action is in almost any scenario. If I'm thinking to myself, should I go to grad school? It's tough to know, how that action is going to turn out until I actually, see the future play out. If I want to know, whether I should jump right now, I don't know how you guys are going to take that until I actually do it. And now I found out that the joke didn't land until later. But that's OK. And the point is that we interact with the world, and we sort of experience the results, and we update how we think we should act based on those results. And this is like the key idea of reinforcement learning. OK, so how many of you guys have seen this video? OK, so this is amazing. Boston Dynamics has taken a full biped and is able to get it to walk around, manipulate all these joints, pick up boxes and stuff. And this video went viral and sort of across the media when it came out a few years ago. But it did not go viral, or at least the main reason that it went viral was not how amazing this robot was. The main reason that everyone was excited about this video was because they were really sad for the robot. Because the guy just keeps messing with it, and the robot doesn't do anything. And for humans, this is deeply frustrating. The robot keeps trying to do the same thing over and over again, and it does not improve its results at all, and doesn't realize that it should do something differently. And it's like the definition of insanity, right? So this is really important. Despite the fact that we've done a tremendous amount of work in mastering the actual technical ability to take these actions, our robots still are not learning the simplest things from experience. If this robot were a human, after a while of getting the box knocked down, right, presumably it would stop and it would ask the guy why are you doing this to me? Or maybe it would do the actual optimal solution, which is you go and you punch him, and then you lift the box and you walk away, right? Okay. So thankfully we have not yet mastered reinforcement learning, but this talk is going to be about how we will. What? That's true, right? Eventually it's who has more computation power, right? Yeah. Okay, so let's define the basics of our environment, or of our problem, right? Every reinforcement learning problem is about an interaction between an environment and an agent in that environment. In our previous example, the environment was the world, right? And the environment encodes what's called the state of the world, right? So the state of the world includes where the robot is right now, it includes where the guy is, where the box is, and every time the environment sort of tells the agent what the state of the world is. And then the agent needs to make decisions about which actions to take, given this state of the world. So for example, oh man, the end got cut off. In this example, the actions that the robot can take are the joint torques that it can make. And there are a lot of actions. And so, and the robot will take an action, and that'll sort of, it'll affect the environment, and the environment will have a new state afterwards. And the robot will take another action. And the other thing that the environment outputs is what's called a reward. Now, a reward can be anything specified by the problem. In this case, probably for the robot, the reward was how high off the ground it got the box, or something like that. And so the interaction between the agent and the environment is everything that we're going to deal with in reinforcement learning. There we go. So we can sort of quantize these interactions into episodes. So an episode is just you start at some initial state, and you take an action, and you get a reward. And then you're in a new state, and you take another action, and you get another reward. And it's a series of interactions until eventually you get to a terminal state. Episode, maybe the episode is from when you turn the robot on to when you turn the robot off. Maybe an episode is, if this is instead like a game of checkers, it's when you started playing to when the game ended. Episodes, so we're going to talk about finite episodes here. Now, the key to every reinforcement learning problem is the transition function. And the transition function defines what the relationship is between my current state and the action that I take at this state and what my next state will be, and what the reward will be at that next state. And we can figure out two things quickly from the form of this transition function. First of all, we're dealing with problems that are Markov, if you'll remember this from the lecture 2 days ago. Now, what this means is that we only care about our knowledge of the state at this time step, and that's all we need in order to decide which state we're going to be in at the next time step. And if you know everything about the world, this is in fact true. Physicists should not quote me on this. But that you can sort of define a distribution for what's going to happen at the next time step given information about what happens at this time step. And similarly for reward. The other thing that is encoded in here is that the transition is probabilistic. So we're not actually sure what the results of a given action are going to be. For example, that robot is not sure what the guy is going to do. And so it's just going to, it's going to try and lift the box, but it needs to recognize that there are different ways that its action can end up playing out with the environment. OK, so this clicker is weird. So let's look at a few different examples of problems. So we have this problem of the robot where the where the state is where everyone is and where the box is and so on, and the actions are the joint torques, and the reward is how high the box is off the ground. We have Space Invaders, for example, where the state is the position of the spaceship and the quality of the shields and the position of the enemies, and the actions are whether to shoot, whether to go right, whether to go left, and the reward is how many ships have you destroyed or something like that. I don't actually remember for Space Invaders. Chess is similar to Space Invaders in the sense that the state is the position of all of the pieces on the board, and the actions are which moves you can make for each piece, but the reward is a little bit weird. The reward is actually 0 for every time step until the last time step, at which point it's either 1 or -1 if you won the game or if you lost the game. And you can actually even model complex human interactions this way. For example, in tech support, you could model the state as the current transcript of the conversation that you've had with the person on the other end of the line, the actions as the things that you can say to them, and the rewards as how happy they sound, right? And so your goal is to make them as happy as possible over the long term. So these are our problems. Now, what's our actual objective in reinforcement learning? Well, what we want is we want to find, oh yeah, good question?
Yes. So in the chess example,
yeah.
you said the reward is 0. Is the expected reward also 0?
The expected reward is not necessarily 0. Initially, right, the expected reward is roughly 50-50. But the actual, we only care about the actual tangible reward that we get from the move. We're going to get to this a lot soon, OK? All right, great. So what we care about is we care about finding a policy pi, which is basically a mapping from my current state to what I should do at this state, OK? That maximizes the sum total of our rewards across the entire episode. Now, pi is just, so we call it a policy. Really, it's just saying which moves we favor in which situations, right? So the robot, for example, probably has a policy where it wants to sort of lower its joints until it can lift something, and then it sort of raises its joints and so on. OK. And this seems like a reasonable objective. We actually have to change this up a little bit, because this particular objective of finding pi that maximizes the sum total rewards has like weird properties when the episodes are infinite. And so basically, like the sum of the total reward is going to be infinite if that's true. And so instead, we're going to have sort of a discounted reward. Gamma is some number less than 1. And it's just going to ensure that rather than taking all of the reward altogether, we're going to sort of focus on the rewards that are on the shorter term rewards. And so as we go farther in time, we care less and less about rewards, but we really care about what's happening right now. So this objective is now a pretty good objective. We want to do things that are going to maximize our long-term benefit, but we particularly care about the shorter-term things that are going to happen to us. In general, gamma is like 0.9, so it doesn't affect it much until we get pretty far in the future. OK, lastly, we need to correct this even a little bit more, because the rewards are stochastic, right? It depends on what the results of our actions are, and so we have to take the expected value. If my policy is that I like to buy lottery tickets a lot, there are some scenarios where I have very high reward, but the expected value is not that high. OK, so there are two major approaches for finding policies, for like figuring out what you're going to do, for figuring out some choice of actions given states. The first is called policy learning, and it is just directly learning a policy. Find some policy pi that takes in S and spits out how good it is to do this, how good it is to do this, how good it is to do this, and then you just sort of sample from the distribution of actions that it recommends, and you're done. And this is the most sort of direct way of learning a policy. This is the equivalent of, if I'm learning to ride a bike, what I do is I get on the bike and I try riding the bike until I successfully ride the bike, and then I'm done. I'm like happy with the way that I ride the bike. I'm not trying to refine, I'm not trying to understand every possible way that I could ride a bike. I just want like a good way of riding my bike. OK, the other alternative is value learning. And value learning is, rather than trying to learn how to ride a bike by just trying it, I'm going to try and figure out like what my expected future rewards are going to be at every time step. Given a certain state and taking a certain action, like given that my bike is at like a 20-degree angle and that my action is pushing down on the pedal hard, what is my future reward going to be like? And so this seems like a more complicated question. Like, I want to now know the value of every state and every action at that state. But it turns out that this is actually the approach that we're going to end up favoring. And this is the approach that has shown to work really well in recent years. So, and specifically, you can convert from a value function that tells you the value of every action at every state into a way to choose a policy by simply taking the maximum action, the best action at a given state whenever you want to know what action to take. Questions so far? OK, so let's go a bit farther into this. So the value that we're going to be talking about all throughout today is what's called the Q value. And the Q value is basically what our expected long-term rewards are, given that we are at a certain state, that we take a certain action, and then after that we do every other subsequent action perfectly. So, if I am the robot and I want to know, OK, if I move my arm up and then afterwards I'm suddenly taken over by a human and the human does this beautiful, graceful lifting motion, how good was moving my arm up? How good a position did moving my arm up put me in? As opposed to, for example, if I kicked the box across and then the human took me over and then the human ran over to the corner and lifted the box. Which of these is better? Whichever one is better will have the higher Q value. The point is that the Q value, it's like a simple idea. The Q value is just the expected future rewards from taking an action at a certain state, given that every subsequent action is going to be perfect, is going to maximize your reward as much as possible. All right. So this is Breakout. This is an Atari 2600 game. It's not a very complicated game. People can play this pretty easily, right? And the actions are move right, move left, or don't move. And the rewards, the rewards are how many blocks you knock out, and because of gamma, how quickly you knock them out. And the state space is where the paddle is, where the ball is, and how many blocks have been knocked out, right? OK. Now let's try and figure out, just for a very simple example, what the given Q values are, and which of the Q values are higher. So here are 2 frames from this game. Each of these is a state of the game, right? It contains all the information necessary to make this decision. Let's imagine that we know the velocity, and the velocity is straight down. OK? Now, in one case, the ball is about to hit the center of the paddle, and it's going to go right back up. And it's going to probably hit the top of the game. In the other case, the ball is falling, and it might actually miss the paddle, but it might also hit the right edge of the paddle. In which case, in Breakout, the ball is going to start ricocheting left. And so it's going to start bouncing, and it's probably going to hit one of the corners. And so these 2 examples don't look particularly different. And so it would be hard to say what their Q values are in relation to each other. So now I'm going to show you guys a couple videos. And I apologize that they're going at slightly different rates. But you can broadly see that these 2 players are playing very differently in Breakout. The player on the left, is just trying to get as many blocks from the center as possible. And the player on the right is trying to make a hole in the corner and then pop the ball up there and then get it to bounce around and quickly knock out tons of blocks. And these are fundamentally different long-term policies. And it actually turns out that the one on the right is much better because it much more quickly gets a very high reward. So if we go back to our original 2 states, the state that is going to make the ball bounce to the corner is going to actually be much better in the case where our long-term policy depends on, where our long-term policy is this go through the corner example. And the state that just lets the ball bounce directly at the center and wants to take out the center doesn't really care about the difference between these 2. And so it's clear that in addition to it just being sort of confusing about how to figure out what your expected long-term rewards are, your expected long-term rewards actually depend a lot on what your long-term strategy is going to be. And so in order to figure out what your expected future rewards are right now, you need to know, to some extent, what your expected future, how you're going to play the rest of the game. And this becomes a bit of a chicken and egg problem. It's actually very difficult, even for humans, to figure out how good an action is, because you need to know all of the actions you're going to take in the future. OK, so the way that we are going to save ourselves from this problem is that we are going to sort of look at this wonderful relation, which it turns out that you are going to fall in love with by the end of this lecture. And this is just a very simple way of relating one Q value to another Q value. And what this equation is actually saying is fairly simple. It's saying that the quality of the expected maximum future rewards for me right now are equal to the expected future rewards of, after I take this action, the reward that I get, plus the expected future rewards for the best action that I take at the next time step. And so this just relies on the fact that every subsequent step is going to have the best possible action taken. And this is a sort of a way of relating between Q values. We don't know what the Q values are, but we can at least say something about how they compare to each other. Any questions on this equation? OK, sounds good. And then at the last time step, right, we don't have any actions. It doesn't matter, because the game is over. And so our expected future returns are just the returns that we're going to get at this time step. It doesn't depend on the action. Now, this equation is nice and all, but it relies on the fact that we know what the optimal Q value is, and that we can set up this relation. And the really cool thing that comes up with this equation, called the Bellman Equation, is that it's actually also, it actually also works when your Q value is incorrect. Specifically, it defines an update rule for us. If we have some Q value, okay, and our Q value, which is again the value in the long term of taking a given action at a given state, and we update that according to this equation, we're actually going to converge to the optimal Q value. Now that's a big claim, so let's take a little while to talk about why that's true. So if I start with some qj, and it's terrible, I assign minus infinity to every value when I'm playing chess, and so I could not possibly be between, I have to be between 1 and -1, and minus infinity is completely absurd. Okay? So in this case, our Q value starts horribly. And in the first update step that we're going to do here, most of our Q values are going to be junk because they're being updated with respect to junk, and so it'll remain junk. Except for the last Q value. Because the last Q value, as we said before, is just the expected value of the return. And so when we do this update equation, we're just going to get that the last Q value is equal to the expected value of that reward, and the last Q value is going to be correct. And so now after one iteration, we have only the last Q values are correct. Now we're going to do this again. And the second time that we do this update, the second to last Q values are going to we're going to say that they are now equal to the reward that they get at that step plus the last Q value, which is correct. And so the second to last Q value is going to be correct. And basically, by repeatedly doing this operation and by repeatedly ensuring that each Q value is correct with respect to, by relying on the previous Q value and updating with respect to the previous Q value, we're actually going to end up converging over time to the correct Q value for every state. You guys have quieted it down a little bit. Anyone have any questions? Seriously, anything. This was really confusing me the first time I did it. Yeah?
When you're talking about getting to the last Q value, is that like you actually play a game of chess and you're like, oh, I made all these moves and I lost, and then I know that that's a -1 at the end?
Yeah. Okay. Good question. So it's more like imagine that I'm at a state which is right before checkmate, right? And now I'm thinking about this last move that gets me checkmated, right? And so now I say, okay, my current Q value, my estimate for how I'm doing in this state is now going to be -1 because I know that in the next move I'm going to get checkmated. And then I'm going to back it up one step further, and I'm going to say, okay, in the move before that, well, if I do that, I'm going to get checkmated in 2 moves. If I do this, I'm actually going to win in 3 moves. And so the Q value for that value is maybe going to increase, right? And so you're going to repeatedly try and update your current estimate for what the best possible future rewards are based on the different the different subsequent results that you see with the future Q values. Yeah.
So when we initialize, we have to make sure that we underestimate all the time. I feel that sometimes it might not be trivial.
To underestimate.
So now you chose minus infinity. If you chose plus infinity, this wouldn't work, right?
I think it would.
The reward would always be higher than any reward you would get in any state.
So the last example would still hold, right? Because in the last time step, your Q value is equal to the expected value of the reward, and it doesn't matter if you initially thought that it was minus infinity, because it's only being updated with respect to the reward that you see in practice. Yeah?
How do you take into account the future Q values for actions if you've never actually taken those actions? And so, like what you said, like if you go back 2 and then you might win in 3, but like let's say you've only played 1 game and you lost, how do you take that into account?
You can't. You have to play every possible game to do this, right? It's going to require a tremendous amount of effort, which we're going to get to in a second. Okay, any other questions before we move on a little bit? Okay. Oh, yeah. To converge? This, I think, would take the number of, the size of the game tree if the game were not stochastic, right? If it were stochastic, very long, this is in fact a problem. Okay, so how large is our space of Q values that we need to estimate? Because we need to find the quality, the expected future returns for every state and every action at every state. So let's look at the example of the state that of the game that we just saw. The number of states in this game is, the number of different ways that you can turn on and off all the blocks, which is 2 to the 96, times, some really ballpark estimate of the number of positions that the ball can be at, and the number of positions the paddle can be at, and the velocity of the ball, which I'm not even including here, and the actions, of which there are only 3. And this already gets us to 2 to the power of 111. And so even if all we do is exhaustively search through the tree, and we know exactly how the game is going to play out, and we update all these Q values, and we do this over and over and over again, we are never going to realistically find all of the Q values for all of the states and all of the actions on all of those states in any reasonable period of time. And so reinforcement learning, to some extent, was stuck on this problem. Yes? Yeah, so the 60s are the position of the paddle and the position of the ball.
So there are 60 of them.
Yeah, I ballparked it. there are probably more than 60. I looked at the specs for this game. I think it's 120 or something like that. This is back in the day. Obviously, if you're trying to play real video games, this assumption gets much worse, right? OK, and so to some extent, reinforcement learning was stuck on this problem of having really large state spaces. Now, this is where I add a disclaimer that reinforcement learning is a field that has been around for many years. And there's been a tremendous amount of progress on it. And with a lot of the hype that's happened recently, some people tend to paper over the achievements that have been done in the past, when really, if you look at all of the deep reinforcement learning methods that have been sort of introduced in the last few years, they all rely heavily on and are basically integrating deep learning into a solution that already, solutions that pretty much exist. And that if you're interested in looking at this field a little more, I highly recommend looking at what people have done in the past. But anyway, traditional reinforcement learning and traditional value iteration, that's what this trick is called, of repeatedly updating the Q values, could not deal with state spaces that were this large. And so instead, in 2013, Google DeepMind decided to add neural networks. And this is where we finally bring this talk back to the actual topic of the class, which seems like a good thing. So what DeepMind did was it basically created a network that would take you from an image to the Q value, from an image, which is the state, to a Q value of each of the actions at that state. And so let's think about, for a moment, if we're a human and we're actually playing Breakout, we're not sort of exhaustively figuring out, OK, I'm at this state and taking this action, and I've updated this Q value, so I think that this is how I should, this is my expected reward at this state. Instead, what we're more realistically doing is we're pattern finding, right? We're saying, OK, I can see that my paddle can reach the ball, and I can see that if I move right, I'm more likely to be able to reach the ball than if I can move left. I can see the number of remaining blocks broadly. I don't care about which blocks remain exactly. I just care about roughly how many there are. If there are half of them are gone, or a third of them are gone, or something.
So was the input to this the actual video?
Yes.
So it wasn't just somebody coded up in an emulator or something the exact state, because they could have done that, right?
No, so it's not. It's exactly not that specifically. Yeah. It's actually learning the representation of the game itself. Yeah, I said that the size of the state space, the number of Q values that you need to estimate is 2 to the 111. If you imagine that actually all of these pixels are changing, it gets much bigger than that, right? OK. So, and lastly, how are the blocks spatially arranged, right? You can see that it's probably not a good idea to aim left if all of the blocks on the left are gone. But you're not doing this exhaustively. And so this is exactly what we want the neural network to do. We want it to look at patterns and using patterns to say how much we expect our future reward to be given that we take a certain action at a certain state. And so let's look at this diagram a little bit more. Specifically, what's going on here is your input is the video pixels. It's going through a few convolutional layers, which we talked about yesterday, that are extracting patterns for us. And then it's going through a few fully connected layers. And then the output is, it looks a little weird. The output, there are as many output nodes as there are actions. And each output node, for example, the one at the top, is the expected future reward given that we take no action. OK? So that's the Q value. That's the Q value of, given that we are at the state and that we are taking the action of do no action. And with the second output, that's given that we are at our state and we're doing up, what is the expected Q value? So it looks a little weird, but the inputs to this network are the state and the action. And the outputs are a Q value. Now, the question that you always have to ask whenever you are reading a deep learning paper or someone is talking to you about a deep learning solution is, what is the loss? Because I showed you this, but we have no idea how to actually get it to find the correct Q value. And this is where we have actually sort of taken, this is like the big step forward, is that rather than, so we can't do value iteration, right? We cannot fully optimize, like we cannot try over and over again to optimize the Q values with respect to each other. So instead what we're going to do is we're going to approximate Q. We're going to say that, we take Q of theta is basically like some parameterization of some function that takes as input the state and the action at that state and tries to, as closely as possible, mimic the actual Q. And specifically, the error that we care about is that we want to minimize the distance between a given Q value, a given expected future reward, and the actual, and basically, if we look one time step ahead, the reward generated by taking that action at that state, and then taking the best subsequent action afterwards. And so we still have this problem a little bit of we don't know what the Q value is initially, right? And so this could be junk. Like just minimizing this distance does not by itself ensure, like if we just pick two random pairs of Q values, I can set them to be equal to, the difference between them is the reward. That doesn't help me much. The point here is that if we ensure that all of the Q values have this relation, hold as well as possible, if for every time step I have the state of the game, and then I know what the state of the game is going to be one frame afterwards if I move the thing right, and I want to ensure that all of these are as close, that the Q values are correct with respect to each other for as many of these as possible, then in the end, that's going to mean that my final result is a reasonable estimate of what my initial result, is a reasonable estimate of what the actual Q value is. And so in doing this, in sort of relating each Q value to each subsequent Q value, we've actually slightly moved towards solving that problem that we had initially, where we want to try and find what the Q value is, but we have no idea what the future holds, and so we have no way of estimating it. And so instead, all we do is we relate every value to every other value, and we try and estimate the future in this way. Yeah? Sure. Why wouldn't everything get set to 0? So everything would be set to 0 except for, so let's imagine that we're playing the breakout game, right? And so you get a reward every time the ball hits a block, right? So one of these times, the ball hits a block, and so the reward is like 3, right? And so the previous, but if we say that the previous Q value is 0 and the next Q value is 0, then this error is not good, because then the error is like 3, right? Because what we want it to be, what we want to be true is we want 0 minus like 3 plus 0 to be 0. Sorry, that's a weird way of saying that. We want the difference between the previous Q value and the next Q value to be 3. Make sense? Other questions? Yeah?
Why do you choose to calculate loss? Or why do you choose to calculate loss after each action you take as opposed to chaining a bunch of actions together into a sequence and calculating loss at the end?
You do. When people actually do this algorithm, they do this in batches. And they take a bunch of actions, and then they sort of reduce. You mean literally like why?
So instead of like being a softmax, like one action being a softmax, like a state that results in after a few actions are taken together.
So this is there is an approach like this, where you slightly increase the horizon of actions that you are sort of optimizing with respect to. And some people have shown that it actually works better. On some level, it becomes like a computational thing. Like how many of these do you want to have to string together? And like there are a lot of trade-offs. We can talk about this after class. All right. Yes?
Maybe it's related to
Sure.
something, but what if the best strategy would be to kind of minimize your performance in the short term so that you get a
Absolutely. So what this is going to do is it's going to basically it's going to say, okay, in the short term, I don't see that my Q values are particularly different, right? And so it's going to keep them mostly close to each other, or maybe even the subsequent Q value is going to be lower than the original Q value. But it's going to, if you look way far in the future, the Q values that you're going to end up with after many, many actions are going to be really high, right? And so the really high Q value is going to be related to the slightly earlier Q value, which is going to be also made really high because this one is really high. And this one is also going to be made really high because this, I may have gotten the hands wrong. But the point is that if you tie all the Q values together, then doing really well at the end is going to make you value higher all of the previous states that did well. And so by doing this, you're actually going to end up relating, the Q values in the beginning that might seem like they're doing poorly are actually going to be propped up by the fact that we know that later on the later Q values are higher. I'm sorry, do you want to clarify the question?
Yeah,
Okay.
so the Q value at an earlier state also depends on the Q value. Okay.
Exactly. Basically, so this holds for t, and this holds for t plus 1, and this holds for t plus 2, and, and so on and so forth. And so you can sort of chain these relations all the way down, because we're minimizing the distance for all of them. OK. Yeah?
Is there any worry that if there's only like a very small number of reward states, that it's like it would be better to just set everything to 0 and have like a massive number of non-reward states all perfectly estimated than to like actually close it?
That is, in fact, a worry. And it turns out that these methods do not do great on chess. And there's a lot of other work that we're actually going to talk about a little bit later that goes specifically into dealing with examples that have very sparse rewards, in which case it's really hard to propagate backwards all the way, all of the, to propagate through a great number of time steps this sort of relationship that we were talking about a moment ago between really long-term rewards and short-term benefit. Although technically speaking, this does actually still work, right? It would just take a long time. And it would be very fickle. OK, so, oh, yeah.
What is E? You said E?
E is the expected value. Sorry. Yeah. Wait, where did I? Oh, no. The episodes. I made up a symbol there. Sorry. OK, so this is the loss that we're trying to minimize, and our actual algorithm is fairly straightforward, right? Oh, sorry. OK, great. So we're going to start out with some theta, some parameterization for our network. We're going to start with some state. And we're just going to repeatedly pick an action from some policy pi. We haven't talked about how we're going to get this policy. We're going to pick an action somehow. And then we're going to get the resulting reward and the next state. We're going to compute, OK, for this action and this state and subsequent state, does our Q value relation hold? And we're going to specifically find the loss for OK, how could we make these Q values more similar? We're going to update our parameters. We're going to set our state to the new state. And then we're going to repeat. We're going to take another action. And so I'm going to try thing after thing after thing. And each time I encounter a transition, I'm going to make sure that my estimate of the future reward is correct with respect to that transition. All right. Do you want to ask the question first? All right. So let's touch on this choice, because this choice is very important. This is going to see, OK, which transitions, which actions do we care about knowing whether they're good actions or not, right? Which ones do we want to update? And you can actually pick any policy whatsoever to update this with. And and anything that you do would be fine. But you could imagine that you actually probably care about picking a policy that specifically does two things. One thing, we want to make sure that we try and update all of the Q values that are close to what we think the current optimal Q values are. So let's say we've run our program for a while, and we know that our player is pretty good at playing breakout, and it's pretty good at hitting the corner for a while, but we haven't seen this one particular or we want to make sure that this particular move is also good, and so we want to try and basically explore and take actions that are very similar to the actions that we think are optimal. But on the other hand, if we only did this, then we would sort of be screwed, because we would find some locally optimal actions, and we would only take those actions. And for example, if our strategy was that we only explored the type of player that hits in the middle, we would never think to play around with going for the corner specifically, and and actually finding that there's this much better way of playing breakout, which is open up the corner and then knock the ball up into the top. And so we want to balance exploration, which is like trying new things, and exploitation, which is refining the things that we have right now. And the way that people do this is actually very straightforward. They just sort of do what's called E-greedy exploration. With like most of the time, epsilon is some small number, much less than 1. Most of the time, we're going to pick the optimal action, or from our distribution, like one of the higher probability actions, according to our current policy. And then some small fraction of the time, we're going to do something completely random. And we're going to see how it goes. And over time, by doing random things, in addition to the things that we expect are going to work, we're actually going to explore a great number of strategies that we might not have thought of originally. If I'm playing chess, every so often, I'm going to try and sacrifice my queen, even though maybe my very simple current chess player thinks that's a terrible idea. And sometimes that's actually the way forward. That's going to win you the game if you're willing to take a risk. And our risk is sort of let's play randomly for a little bit. OK, so all of these things together lead us to this player, which, if you didn't know beforehand, is a neural network. This neural network figured out, after something like 400,000 batches of iterations, this takes a while. QE learning is not a fast process. It figured out basically a really good, pretty optimal way of playing a fairly complicated game with a state space that it didn't know ahead of time. It had no idea how complex this game was. It's only going off of pixels, and it was able to really well estimate, the quality or the expected quality of your action for all future states, and sort of bias its actions towards those expected positive results. OK, so this is great and all. It actually, when DeepMind originally did this, this came out in 2013, they played all of the original Atari games, and for roughly half of them, they actually outperformed the human professional players. They actually broke 2 games. The boxing video is fairly amusing. They managed to trap a person in a corner and just repeatedly button mash, which no one had found the solution to. And this is great. We have computers that can play video games. And video games are sort of a microcosm of reality, right? You have states and actions and rewards, and they're sort of well structured. And it's pretty cool that we can, for the most part, solve this problem now. Solve at least the Atari problem, which is a simple version of a video game. Now, before we go any farther, I want to highly, highly recommend to you that you go to selfdrivingcars.mit.edu/deep traffic. This is something designed by the 6SO94 team. Lex was your lecturer yesterday, and he was the lecturer for that class. And it's awesome. It takes you about 10 minutes to get started actually playing around with a deep Q network and actually seeing the results update in real time. It's really fun, especially considering that these things are a little bit hard to get to work by yourself, or at least that they take a little while. It's really fun to start it and basically get to play around with parameters, and it's all pre-built for you, and you get to see your car driving through traffic and in real time learning how to react to different traffic conditions and try and make it go as fast as possible. Seriously, click on this link. The slides are online, or just type it in. I highly, highly recommend it. OK. Now, deep Q learning sort of opened up this whole field of deep reinforcement learning that has gotten people increasingly excited. However, there are still, so basically you can chart the evolution of the field of deep reinforcement learning by looking at what deep Q learning does not do well. Because a lot of the research for the last 3 years has been oh, you know how DQN totally couldn't do that? Well, now we can do that. And to some extent, it's still being driven this way. So let's talk about what deep Q learning cannot do. All right, so the first problem that we have is that we have a set of very, very restrictive assumptions. One of the things we assumed was that, for example, our state fully encapsulates all of the information about the world, and that therefore we can choose an action based only on the things that we can see right now. And we know that this isn't true. Take, for example, a first-person shooter, right? You're walking around the game, and the only thing that you can see at any given instant is maybe a corner or something like that. But we know as humans, we have some idea of the layout of the world. And so we want to somehow encode information that we have seen from previous states for the later states to make decisions based on them in the later states. Now, you guys can probably remember a method that does this. We're just going to take our deep Q network, and we're going to add an LSTM layer. And what the LSTMs are going to do is they're just going to take, they're going to have us remember sort of portions or characteristics of the state from previous time steps and feed them into our subsequent time steps. And so you can imagine that in this case, it's feeding in like, oh, I remember there's a door behind me, or something like that. And then you can see that it goes to the corner, it picks up an apple, and then it remembers to back out and sort of keep exploring. And so this is a big deal because this sort of extends us to a much wider class of problems. Another thing that has happened, another problem with DQNs, which someone mentioned here, is that it does not do that great with really long horizon problems. And what a long horizon problem is, right, is like it's a problem where I take an action and I only find out much later whether this action has, was actually a good idea. And so when DeepMind built AlphaGo, this was sort of the major problem that they had to encounter. There is a signal, and the signal happens after like, I don't know, like 250 moves or something like that. And you have to take a lot of actions before getting to that signal. And you cannot reasonably like explore the space of actions in any sort of time-efficient way such that we would actually, get to a reasonable result with only a Q network. And so instead, what DeepMind did in order to try and address this problem, and successfully address this problem, is they combined this sort of, deep learning with a traditional search structure. A traditional search structure is just like, I'm going to look at this, like my board looks like this right now, so what if I did this, and what if I did this, what if I took this action or this action, okay, what if I took this action after that action, and so on, and you sort of search through the actual game. And the way that deep learning factored into this is that it used sort of networks to look at the game and to sort of try and estimate very quickly, like, okay, what do I think the future rewards are from this action? And what do I think the future rewards are from this action? And okay, I'm going to bias my search. I'm going to try this one first, right? I'm going to try this thing that my neural network tells me might be a good idea, but I'm going to search through it sort of like using this more exhaustive method. And it turns out that by combining these two approaches, you're actually able to leverage both the like feature identifying qualities of deep networks with the really nicely structured, with the nice sort of structure to solve much longer horizon problems. This works really well, and people are now starting to apply it to other problems like I think air conditioning, or air conditioning might have been DQNs. Anyway, it's a very powerful method. Okay, the last problem, and arguably the biggest problem with reinforcement learning, is that it requires a simulator. I have to be able to take actions and see the results and decide, like whether those actions went well or not, and take more actions subsequently. And if you imagine that now I want to train a self-driving car using deep reinforcement learning. And so I put my little robot behind the wheel, and I tell it to start driving, and at first it starts driving, and it's doing okay, and then it's doing eager exploration, and so it takes a left, and it's in the middle of a freeway. And it crashes, and everything explodes, and the reward is negative. So in this case, clearly, like even if we do technically have a simulator, we can't really use the simulator to explore as much as we would want to. Now, I tried to think of like what's a good example to put as an image for why there are real-world consequences to taking an action and seeing how it goes. And I figured that this was a reasonable. This is the don't try reinforcement learning at home, right? Anyway, so there are a few approaches that are being sort of taken now to solving this problem of either it being very computationally expensive or just taking a long time to try things out in the real world. So one of them is I'm not listening. I don't care. I'm going to do the thing in the real world anyway. And this actually does work. There is a group at Berkeley that managed to train a robot to pick up objects in a box by basically getting like 16 robots in a room together and just for like 4 months repeatedly just lowering having the robots lower their arm, try and pick something up, and rinse and repeat. And after 4 months, they actually learned a really cool, they have a reasonable ability to, using an image, move their arm and navigate and like pick things up. And that's like pretty cool. That's not a simple problem to solve. And they, to some extent, made a huge amount of progress on it. But it requires 4 months and 16 robots and so on. And it's still a very constrained environment. Another option is that you just build really, really nice simulators. And so, graphics in computer graphics are becoming crazy these days. And there are some video games that you can make, arbitrarily close to what reality looks like. And you can just play around in these video games and repeatedly try and take actions and see the results. This is sort of a dangerous path to go down because you're probably never going to be able to fully and correctly simulate the entire real world in a way that would be satisfactory for like someone who's actually trying to make sure that, for example, a self-driving car is safe. Now, the last option, in my opinion, because this is my research, is the most exciting option, which is the idea of transfer learning. So imagine that we have successfully trained our agent, and our agent can now do well on playing Breakout by seeing where the ball is and then bouncing it up and so on. And now we tell it that we want it to play Pong. There are a bunch of differences between these games. One of them is rotated 90 degrees. The objective is completely different. But if you're a human and you're an awesome Breakout player and someone tells you to start playing Pong, you're like already much better at it than if you had never seen it before. And the idea here is that you can take features from your original game and you can take logic that you built in your original game and bring it over to another game to learn to play that game much more efficiently. This works. People have published papers about how this particular, you can train a network much faster to play Pong if it's already played Breakout. Or maybe it's the other way around. OK, now this is really exciting, because imagine if we do this for reality. The game on the left is GTA 5, and the thing on the right is reality. They don't look that different, but they are different in subtle ways. So if I train my reinforcement learning agent on GTA 5, and I get it to be really good. And in fact, a month ago, OpenAI published the Universe, which is sort of an environment for playing around with basically any game you want, but GTA is one of them. And there are people working on getting self-driving cars to work using reinforcement learning in GTA. If I can get a really good agent, and then all I need to do is to learn a transfer from this really good agent to reality, that is, theoretically speaking, a much easier learning problem. And so it's going to require far fewer examples. And so if I can get really good at transfer learning, and I can train my agents to do all of this work in virtual reality, and then bring it into actual reality, then I can basically solve the problem that we started out here with, which is of getting complex agents to interact with a real environment and to learn both from the real environment and from their simulated experiences how to interact with our world. That's reinforcement learning. Any questions?